My talk today is partial regularity of sum and intersection of power of monomial ideals. The first we recall some definition of regularity and some related invariant here. Throughout my talk, I only consider R to be the polynomial ring over a field K. We let M to be the maximal homogeneous ideal of R. We let R M to be a finite generators R module. Then we define the AI invariant of M to be the number A, to be the subprimum of T such that the local cohomology of M at degree T is non-zero. And then we define the Casanova-Mumford regularity of module M to be the max AI M plus I for O. Besides this, these invariants, we also mention here to another invariant for S. We define the partially Casanova-Mumford regularity of M to be the sub. because this number may be minus infinity, and we define the other s m to be now we let I a homogeneous ideal of n. And then we have some beautiful zeros about the symptotic behavior of security of power of n as follows. The first result proved by Gatkowski, Herzog, and Trung. About 1999, and independent by Kudialam. This result say that this result say that the regularity of power n time n to be
this n zero, not for all.
Yes, no, yes. This is this become this is linear function of n for O and big enough. The same zeros for two invariant was proved by Trung in Lysa's. Also positive. Yes. But if we consider the saturation of a power ideal, the result is not true. If we we consider the student. And then Katkowski. The result of Katkowski, I and Lazarsfeld say that. They prove that this limit does exist, but and this causes a subsidy constant. But this number may be not a rational number. The example for the variety which will be defined by an ideal such that this limit is a rational number was constructed by Katkowski, and from this and note that we note that the regularity of this module defined by this formula, and this shows that it's invariant. This means AI yes.
So in the world of Costi, I understand. So is there some example of the limits?
Yes.
With the
This example was
not always. Not only.
yeah.
It's only
Yes.
in the first paper.
Yeah.
From this we can exit, but the first example for AI and it, for the first paper say that this is not a function, a linear function of n for O n big enough. First pointed by Katkowski, Herzog, and Trung in this paper. But the example for the limit is unrational number was constructed by Katkowski. Because this function needs not a linear function of n when n big enough, and in this talk I consider following question here. The first is what is the asymptotic behavior of this invariant of n. and 2 is we only consider the question 2 is when is does this limit exist for monomial ideal. In this context, we consider a bit general slide of the question above. We let Ln to be the monomial ideal. Then the first we prove that follow. The first we define some special function here. The first we define the periodic function. At usual, periodic function from the natural number into the rational number maybe has minus infinity value. This function is called periodic with and we define another function is called quasi-linear function. the periodic function f defined by this way is equivalent to say that there are the number alpha n. Such that if we have n is concurrent to I mod n with I, then we have fn equal to alpha I n. With this definition, we have the following zeros. The first is the first. So first we have z invariant is a linear function, is quasi-linear, quasi-linear function of n when n big enough. And the two is exit we only prove the theorem one for the case the index here is d, and if we replace the d by arbitrary index I, we do not know the limits exist or not.
Excuse me?
Yes.
So you make a notation Ln like this.
Yes.
So for arbitrary monomial ideal can decompose like this one?
No. This is more. This is a bit general in for this question. If we consider the case only one seat, and we have the context here. You can have one. You can have this one monomial ideal if every another is zero. The limit set can we can prove for every index here when we consider the integral closure of monomial ideal. We have the first way is equals the definition of integral closure of J to be the ideal consists of O polynomial f of R such that f satisfy an equation is of the form and in this case we consider the monomial ideal Ln star to be first one. If we consider the interclosure of the power of this ideal, and here we remove an ideal I. Then we have the first statement like the same as this. And the second is stronger than this one. In this case, we give an upper bound for this invariant. And from theorem high, we have a immediately consequence say that the third theorem have some very interesting consequence. The first, if we consider the case if I is a Stanley rational ideal. If I is a Stanley rational ideal, this means I is generated by a square free monomial. Then we have a primary decomposition of phi is of the form where in this case pi is primary ideal generated by a subset of variable. Because pi is generated of variable, and then we have pi and is integrand closure means that for oi for in this case we have the symbolic power of I is PIN, and in this and by theorem 3 we have the following.
n is the intersection of pi symbolic power n or just
Yes, symbolic power n is equal to this,
equal.
and because this equality we can have.
So this here n equal to I. Is it equal to I?
No,
No.
no.
Oh, I'm sorry. I'm sorry.
Yeah.
Not equal to I. Eventually,
Yeah.
we should recall the definition of symbolic power in the general case. I mean, for not only for square tree ideal, but also for any monomial ideal. And then one can understand why we consider also Ln. And also Ln as star. Okay. So just not. So our study is related to symbolic power of all monomial ideals, not necessarily for square tree. But for the square tree, we get the nicest one.
And now if we consider the case I is a monomial ideal, and then in this case we can consider the special case of the theorem 3. There for only integral closure of power of I, then we have
not quite lim.
yes. This fact is proved first by result of Herzog, Trung, Katkowski, Herzog, and Trung. Here I only state this here, but we prove here we prove only the second statement say that. Here we only
Here is your
here we only
and for all them.
yes. The first statement was proved by Katkowski, Herzog, and Trung, and in my talk we only prove the second statement about the bounds of regularity of integral of IN.
So n is bigger enough, and it is equal to p times n plus p, or
That's,
if moreover this is true for all small n.
For all them.
for all, yes, for all. To
So regularity,
Yeah.
if n is large enough, then it's equal to some
E and a plus E,
Yeah,
where
plus-
E is between 0 and D.
Yeah.
p times n plus e, right?
P times N plus E, where E is between 0 and D.
yes. To have some feel about this, we consider an following example here. In this, first we is in this case to to compute the regularity of this, we can use the figure here. we know that all monomial of in, for example, is all if we if we identify this monomial with the point ml in the plane r square, then we can easily see that all point all monomial of in is lie in the it's lie in the this side of the line of this line, and all monomial of ideal I2 lie in this side of this line, and then if we in this case we can have dimension of I mod n is 0, and when we time with n, we have this means that we can time n here, we can n a, and we can n d here. And we can easily see that every monomial of this ideal lie in the figure, and from it we have ELN equal to for ON, and this means that this regularity is not a linear function of n for ON big enough, and from the we can easily to see that the regularity of I1n and equal to E2n is 2n minus 1, and from the from the exact sequence of the form we can see that and this function is linear, but this is not. This is all of my talks. Thank you for your attention.